In May 2026, the Artemis II mission sent humanity back to the moon's neighborhood for the first time in over 50 years. Watching Orion glide over the surface, it felt like the hardest part was behind us. The momentum was building, and the stage was perfectly set for the real prize. Naturally, all eyes turned to Artemis III. This was supposed to be the mission where boots finally touched lunar dust again. But looking at the official trajectory document, the plan abruptly veers off course. The historic lunar landing for Artemis III has been entirely canceled, pushed back to Artemis IV. Instead, it has become a 2027 Earth orbit demonstration mission. We are staying in our own backyard. To the public, this looks like a massive setback. But staying in low Earth orbit follows the oldest, strictest rule in spaceflight. If you want to survive the vacuum of deep space, you have to run your tests where you can still ask for help. To understand why NASA is hitting the brakes, we have to look at how we learned to survive up there in the first place. Long before we risked sending a human into the void, space agencies used a biological sandbox. They needed proof that living cells could survive the journey. The very first incremental steps happened in 1947. Scientists packed ordinary fruit flies into captured V-2 rockets and shot them into the upper atmosphere, just to see if they could recover them alive. Once the insects made it, the tests escalated. By 1961, Ham the chimp was strapped into a specialized flight suit to prove that a complex organism could survive the intense physical forces of a capsule launch and re-entry. Proving we could survive was only the first hurdle. The next massive challenge was figuring out how to build and maintain infrastructure in a weightless vacuum. We needed an infrastructure sandbox. The ultimate test of that infrastructure is the International Space Station. The political directive to build it was laid out by President Ronald Reagan back in 1984. But writing a speech and bending metal in orbit are two very different things. This timeline charts the construction of the ISS. It required a grueling, decades-long buildup. It started with the solitary Zarya control module in 1998, and slowly, piece by piece, expanded to include international labs by 2008. That is how human spaceflight works. We don't magically construct cities in orbit. We stack successful, incremental tests on top of each other until we have a working station. Both of those sandboxes existed in low Earth orbit. If something went wrong, the astronauts were just a few hours from home. But deep space is entirely different. Millions of miles away, the safety net disappears. This chart tracks the success and failure rates of early attempts to reach Mars. The red sections represent the devastating 60% failure rate of those initial probes. Over half of everything sent either missed the planet, burned up, or crashed into the surface. We did eventually figure it out. Probes like the Viking lander successfully touched down and beamed back these alien rocky landscapes. But those early brutal losses taught aerospace engineers a painful lesson. This massive risk profile forced engineers to rethink hardware development, making exhaustive Earthbound testing mandatory for deep space payloads. Look at the James Webb Space Telescope. From its conception to its launch, it endured a grueling 30-year timeline. Scientists subjected these delicate gold mirrors to years of extreme cryogenic freezing and intense vacuum testing before it was ever allowed near a launch pad. A million miles away, a stuck hinge or a software glitch is instantly fatal. Every single point of failure must be engineered out before the countdown begins. Which brings us back to the Artemis III mission trajectory. When you look at this document through the lens of history, that pivot to an Earth orbit demonstration is a textbook risk mitigation strategy. We are dealing with highly complex mechanics that have never been tested together. Step 3 highlights rendezvous and docking tests, involving brand new commercial landers built by SpaceX and Blue Origin, alongside novel crew transfer procedures. By keeping these unproven systems in low Earth orbit, NASA is holding on to the ultimate safety mechanism. If a commercial lander's life support fails or a docking collar jams, the astronauts are still within hours of a direct abort pathway back into the Earth's atmosphere. We have done exactly this before. The Gemini program spent years in Earth's orbit, meticulously practicing how to dock two spacecraft together in a vacuum, long before Apollo 11 was ever cleared to aim for the moon. We love the image of the fearless explorer leaping onto a new world, but that final step is the result of a long process. The ability to safely walk on the Moon or Mars is entirely dependent on the quiet, methodical homework we are choosing to do in Earth's orbit right now.